We'll be starting in 5 minutes.
Do a quick sound check. Sound check.
Yeah, I can hear you.
Okay. Okay, so it's 5 after the hour, and let me welcome everybody out there in internet land and the MIT students. And as Dave puts up the notebook for today's lecture, let me just say a few words of introduction. So We are now moving into module 3 of the class. If you go to the class page, you'll see that we're starting a new section with section 3.1. And perhaps in a way, this is almost like starting a new half course, like the second half of a course where, maybe students could kind of join in here. We might mention some things from before, but I think it's almost like a separate quarter class or so. And this is a bit of an experiment, and we'd love to hear what you think about it. But, as with the importance of climate science and we're all, as we think we're getting COVID under control, maybe hope we're getting COVID under control right now. The real big issue, the next big physical issue, or I don't even think it's next, the big issue is going to be controlling our climate. And we have this belief that there are many folks, students of computer science, students of mathematics, who would like a little bit of an introduction in the computations that go into climate models without all the heavy details. An introduction, really, for starters, to because people talk about climate models and people talk about whether you should believe them, but it's even hard to know what you're talking about without any familiarity. So with that in mind, what we're trying to do in this now, I mean, it's not quite half, but we'll call it the second half of the course, is give sort of the necessary insights for the next week or two so that we could bring up basic climate models so that anybody with a computer science background, a math background, other backgrounds, statistics backgrounds, can participate in climate science modeling. So with that going, Philip's already excited about getting into climate science. That's not today's lecture. Today's lecture is going to be just the differential equation background, the continuous background. But that's where we're heading, into climate modeling, given how important that is. So, Dave, take it away.
Okay, thanks, Alan. Hi, everybody. So as Alan said, we're going to be moving towards climate modeling. And as with many models from the sciences, in particular physics-based models, these are often written in terms of differential equations. And so today we're going to start with ordinary differential equations, or ODEs. But we're actually going to not start with ODEs. We're going to see how ODEs actually can arise from more intuitive discrete time models. And then at the end, we'll go backwards and say, well, if I am given a differential equation, how can I actually solve it on a computer? And we'll find that we get back to where we started, which is what we call time stepping. So that's what we're going to look at today. So we're actually going to start with, as always, with the sort of simplest possible model that we can. And it's going to be modeling component failure. So you may remember that a few lectures ago, we did a model of component failure starting from a probabilistic or stochastic model. So even if you didn't see that, it doesn't matter. We're going to sort of restart from a different point of view with a model that we derive from that probabilistic model, but it's also a pretty intuitive model in its own right. So what is this about? Again, it's about light bulbs or other mechanical components or electrical components. And the question is, how long does it take for light bulbs to fail? So if we're in a factory and we have, thousands of light bulbs, they're just going to start failing. And we want to sort of keep track of how many light bulbs do we need to have in stock to replace those light bulbs that failed. How long do they take to fail, etc. And so we'll start off with the simplest possible model as usual, which is just that every light bulb, again, has the same probability to fail each day. Except that light bulbs don't really fail, at midnight each day. They fail at some point during the day. But to start with, we'll just count at the end of each day, we'll count how many failed during the day.
Isn't it true that light bulbs fail and other bad things happen when you most need them to not happen, right? Isn't
that's also true.
Component to this?
That's somebody's law, yes. Okay, so we're going to have this sort of checkpoint every day, once per day. So we have a sort of integer time going on. So we'll call the number of days k. And at the end of day number k, we'll ask how many light bulbs are still functioning, which we'll call capital N sub k, right? So let me zoom in a bit. So we have capital N sub k, then N for number, and k is which day we're on. And so we'll start with an initial number, capital N sub 0. And so what we want to do to model the situation is to find a formula that tells us, well, if I know that I have n sub k on day k, how many will I have on on day k plus 1, which is n sub k plus 1. And to get that, what I actually need is to work out how many are going to fail on the kth day. And so let's call p the probability that each bulb fails each day, as I said. So as an example, let's think of 10% of the bulbs failing each day. So that's, pretty shoddy, bad quality light bulbs. If we have to replace them, if 10% are failing each day, but it's just an example, then that just means that the probability p will be 0.1 for each bulb. So for example, if there are 100 bulbs altogether and 10% fail on the first day, then, well, how many are failing? 10 are failing, and so there'll be 90 left. And in general, if we generalize that little calculation, then if a proportion p of the nk total fail, then how many do we expect to fail? We expect p times n sub k to fail. So, if you remember back to the probability module, this is actually an average of a binomial distribution, but we won't. We don't actually need that level of detail. We're just sort of doing basically a macroscopic model, and we're saying the proportion that fail is p, and so the number that fail is p times nk. Of course, this might not be an integer, and so you might be worried, well, what does it mean to have a non-integer number of light bulbs? But it's just a sort of, on average, if we repeat this experiment many times, on average, what will the number be? It can be 3.14159. As an average, that's perfectly fine. And so we can now write down a formula that tells us how this quantity changes in time. So time is this number of days k, and we get to the number on day k plus 1, or at the end of day k plus 1 is the number. So this is the number that is still working, that is still functioning, that have not failed, is the number that had not failed at the previous day minus the number that failed during the day. And we just worked out that that's p times nk, and so we get that the nk plus 1 is the number from the previous day minus p times the number from the previous day.
And as many students will recognize, this is a very simple recurrence, right? The word recurrence comes to mind when you see.
Yeah, so recurrence or, So we can actually rewrite this in a slightly different way just by moving the nk over to the left. And that has the advantage that it now has this quantity, which is the change in time, and that will be important later. The change during the k plus 1th day is minus p times the times the total number at the start of that day.
And again, I'll just interject a minor comment that I'll say something that's probably not actually 100% true, but when people do discrete models, very often they'll write it the first way. What happens at the k plus 1st step in terms of previous steps. It's only when you start thinking about going towards the continuous that the second way, the difference starts to look a lot more attractive.
Yeah, we'll see that. So,
but of course, we're always trying to get people to think discrete and continuously at the same time.
Right. So in this particular case, in this particular model, we can actually solve the entire thing analytically and get a formula that tells us how many bulbs are still alive at time k. So if we rewrite it the same equation in yet a different way, which is nk plus 1 is 1 minus p, all multiplying n sub k, just by factorizing nk in this formula up here, then we get sort of this. We can expand each step going downwards, and we finally end up with the number at time k is the initial number multiplied by this factor, 1 minus p to the power k, that's decaying geometrically or exponentially fast. Why is it decaying? Because p is a number between 0 and 1, because it's a probability. And so 1 minus p is between 0 and 1. And so when we take powers of that, it gets smaller and smaller as we take bigger powers. So that's the simplest possible case where we check at the end of the day how many have failed. Now, what if we check every half day instead? So, or in general, we're going to check n times a day spaced equally during the day. So how many light bulbs fail in half a day? So let's go back to our example. If 10% fail every day, how many fail in half a day? Well, it's natural to think that, in that case, 5% are going to fail in half a day. But that's not actually quite right because of the effect of compounding. that we know from compound interest. This is basically the same thing as compound interest, except here it's not interest, it's sort of anti-interest. You're paying a loan to the bank. So if 5% fail, and then we're left with some number, and then 5% of that remaining number then fail, how many are we left with at the end of all of that? You can actually do that calculation easily. So 5% fail, we're left with minus 0.05% or 95%, and then we have 95% of those failing. Then the result is that the total number that we have left is 0.9025. So that's slightly more than 90%. So slightly fewer have actually failed than the 10% we were looking for. And that's due to this compounding effect that we're taking a percentage of a percentage. But it's actually pretty close to 90%. So it seems like a reasonable guess that we should, or a reasonable thing to do, to take 5%. It would be possible to calculate exactly this proportion that we need in order for the compounding to give exactly 10%. That is possible, but let's for the moment just do it like this. So we're going to say, okay, instead of 10% failing once a day, we'll have 5% failing each half a day. So let's generalize that again. So suppose that we're checking now n times a day, equally spaced during the day. And we're going to say that a proportion p over n fails, during the 1 over n period of a day. Right, so before we had probability p failing each day, now we're going to have probability p over n failing n times a day. Right, so you might think again that adds up to a proportion p failing during one day, but that's not quite right for the same reason that we just saw. So let's actually see what happens if we do that though. So we can again write down some formulas. So here we're using a bit of a strange notation. We're indexing now with not just the integer k, but sort of the fraction, which is k plus this 1 over n piece. So that's sort of the next mini step during a day, but it's still discrete, so we still can write it using an index. And so that's just given by 1 minus p over n times the number at the start of the day. So it's exactly the same calculation that we did before. And now we have to do that again and again during one single day for n steps. And so the result at the end of the day is nk plus 1 equals nk times 1 minus p over n to the power n. So we get this compounding effect coming in here. So we could also write that instead, although we're still in a discrete situation, as we had a video a couple of lectures ago about discrete and continuous, and one of the examples was, well, indexing into a sort of vector is basically the same as evaluating a function. So you can think of it either way, and we'll start to use this notation more as we move towards a more continuous point of view. So yeah, okay, so we actually have this formula though for what happens if we are checking with, so the model is actually changing a bit because now we're having p over n failing n times a day. So let's just, this is a lot of formulas. We don't really get what's going on. So of course, as usual, in a computational thinking course, the obvious thing to do is to plot to see what's going on. So let's do that. So this is what we get from that formula if we if we check what's happening once per day. This is the nk as a function of k. We see a nice sort of exponential drop off. And now I have a slider up here, which I'm going to move, and that's going to be the number of times per day that I'm checking. And it's not working.
Yeah.
Okay, so here's checking now twice per day.
Why is the n off by 1?
Because I'm taking 2 to the power n number of checks per day.
Oh, n is 2 to the first.
Yeah.
I see.
Yeah.
Okay.
Yeah.
You could put in, it's a string. You could actually put in.
Yeah, so it says right here.
Okay.
Two times.
But you could put in the slider string, you could go 2 hat. Right after the equal sign. Right after the equal sign. The first equals. Yeah, just go 2 hat. Nope. After the equal sign.
After the equal sign.
Right. Before the dollar.
Right.
Two.
Oh, I see. I see.
There you go. Now I'm happy.
How that? Okay. Okay. Yes. Thanks. Good. Yeah. Good idea. Or I could do, yeah, whatever. Yeah. Okay. Let's not fiddle too much because it'll all break. So I can, yeah, this P is fixed. That's the probability, that the original probability of decaying for each light bulb each day. And now I'm going to use that same P, but do this P over N decaying N times a day. So, okay, so here we go. So this is twice per day. So you see that indeed we get a different result as we thought we would due to the effect of compounding. But it's, kind of close. It's not too far away. And so let's see what happens as we just increase the number of times per day. So again, it sort of, the curve moves up and we get more points because we're checking more times per day. And then as we keep increasing, the curve moves up more. And so you might expect the curve to keep moving up and moving up and moving up. But as I increase the number of points, it actually sort of stops moving, or, asymptotically stops moving and comes to a sort of standstill. Let's increase this. Let's allow even more points and hope that it doesn't take too long to calculate and plot. Okay, there we go. So there's 1024, and you can see that the last few times it was recalculating, basically it gave me exactly the same curve. And so this is, if you think back to the class about the discrete and continuous, what seems to be happening is that we seem to be actually converging to something that that exists independently of any kind of discretization, and that we can give a name to and calculate. And so this is the kind of continuous limit of what happens as we take this, as we check more and more times per day, and we take, the probability to fail smaller and smaller in the right way, which is this P over N. Okay, so how can we actually take that? Let me just move the slider back so that my notebook's not too slow. Oh dear. Okay, so how can we actually define this continuous time limit? So we have this formula 1 minus P over N all to the power N. You might recognize that from calculus. That actually has something to do with exponentials. And so again, it's compound interest, and that also gives rise to exponentials. So let's look at that in a different way. So what we've been doing is taking, a proportion P over N to decay in a time 1 over N. So basically what we've been doing is taking time steps, small time steps of length 1 over N. So let's call 1 over N something which is delta T. Delta meaning sort of a little change in T. And we'll think of that literally as the time step that we're sampling going and inspecting our light bulbs at. So let's write down a more general formula that depends on this delta T now. And the point is that we see that what we've been doing is, well, we're actually multiplying the P by delta T. This delta T is this 1 over N here. So we're actually multiplying P by delta T. And so in general, the formula is going to be something like this, or going to be exactly this, that the number at time T plus a little bit, plus a little time step, minus the number at the previous time step equals minus the fraction that have, the proportion that have decayed as P. And so we actually multiply that P by delta T, the length of the time step, to get the sort of the actual, to get the total fraction that have decayed. Multiply, and so the total number that decay is that fraction multiplied by N over T. So it's exactly the same idea as we've had so far, but now just sort of with this slightly more general notation with this delta T. But this delta T is kind of annoying because it is sort of getting in the way. We don't really understand its effect. So let's actually put all the delta T's together, group them all together into the left-hand side by dividing through the whole equation by delta T. And we get this expression, N of T plus delta T minus N of T, all divided by delta T equals minus P times N of T. And hopefully you recognize this left-hand side. This is almost the definition of the derivative, as we saw a few lectures ago. And it will become exactly the definition of the derivative if we actually take a limit where delta t goes to 0. And so then that becomes exactly the derivative of n of t. So if we take that limit and write the new equation out, we get that the derivative of n with respect to t evaluated at time t is equal to minus p times the number at time t. And where n at time 0 is the initial number n sub 0. So this is a differential equation, an ordinary differential equation. What is a differential equation? It's an equation that relates a function to one or more of its derivatives. So actually, we're saying, oh, my function n of t that satisfies this model that we came up with should satisfy this equation where what it's telling me is, if I'm at a particular point if my population of light bulbs is a particular value right now, it's telling me how that value will actually change in time, sort of instantaneously. So it's it's a pretty actually difficult concept, but so personally I find it much more intuitive to think of this about this discrete model. But then if we actually go back to this curve, we see that indeed just taking the discrete model and then having this sort of more or less natural idea that we can take, that we can check, that we can look what's happening at smaller and smaller time intervals, we're sort of naturally led to this limit, and that gives us this differential equation formulation. So that's how you can think of differential equations as arising. And then the question is, well, now that I have this model, how can I actually solve it? So again, because we have such a simple system now, such a simple model, we can actually solve this one analytically too. So what is this saying? It's saying that I want a function such that when I differentiate that function, I get something that is proportional to the same function. And that is another way that we can define the exponential function. And so the solution, the exact solution of this differential equation, which in general we won't be able to do, but because it's such a simple one, we can actually find the exact solution, is that the number at time t is the initial number multiplied by this decaying exponential curve, exponential of minus p times t.
Can I say a word or two about the word solve? So
which word, sorry?
The word solve.
Solve, yeah.
Yeah, because I think the very first time, maybe I was an undergraduate, I heard, solve a differential equation, and I found the word solve a little confusing. Like, I knew how to solve x squared equals 2, like, square root of 2, maybe minus square root of 2. And you've already used the word solve in terms of solving a recurrence, and then you talked about solving a differential equation. And could you put that nice curve back that you had with the limit, just above your... So just to be clear what solve means, and forgive me if I'm just saying the obvious, but when you're solving the discrete equation, what it means to solve the discrete equation is, here, let me even grab some buttons here. It actually literally means to find, you're starting at 100 as n0, and you're basically finding for all days, right? You're finding these points, right? That's solving, means finding an expression for all of these dots, right? And then what does it mean to solve a differential equation? It means basically finding an expression for this entire smooth function.
For any time t.
At any time t, right? So
which is a real number now. Any real number, any fractional number of days, we can find a.
So I mean, I don't know whether this is sort of obvious, but like, in grade school, you learn how to solve a linear equation. There's one answer. You solve a quadratic equation. There's two answers. When you solve a recurrence like this one, you get an answer for each and every day. And when you solve the differential equation, you get an answer for, as Dave just said, for each and all of time. I thought it was just worth pointing that out. I mean, maybe it's obvious, but
no, that's a good point. Yeah, so because in the case of the discrete recurrence, we only have a finite number of things to calculate. In this case, 20.
Well, yeah, but there's really infinitely many.
There are really infinitely many, but you usually can't calculate more than a finite number.
Well, you wrote down the solution for all k.
In this particular case, yes, but it is usually the case that you can't.
In the integer case, there are countably infinite points, and in the continuous case, they're uncountably infinite points that you're solving for.
Yeah.
That's right.
Definitely. Yeah. Yeah. So what we want to be able to do is, yeah, exactly. As Charles said, find the value, find the height of this curve at any input t, at any real number t. We want to, to be able to say, oh, at time pi, the number is exactly, e to the minus p times pi or whatever times the initial number. And for some differential equations, we can do that and write down an explicit formula. That's what we mean by solving analytically. An explicit formula, like I did, for n of t. If you put pi in here, you get out the exact explicit answer.
Analytic solutions are for pre-computer days, or for maybe for professors to grill students. Otherwise, who cares about analytic solutions?
Right, exactly. So let's look now. Okay, so well, first of all, let's just check that this does give the right thing. So this is the same graph again, but now I've added in the exponential. This green curve is the exponential solution of the continuous time system. And as we increase the number of times we're checking per day, we see that indeed this curve converges nicely to that exponential limit and just sort of gets closer and closer and closer. And you could go away and actually I should have done that. You should, homework, calculate how far away the discrete curve is from the exponential limit and see how that changes as you change the number of points you're taking. So that's telling us about how fast, what is the rate of convergence towards that limiting object curve. Okay, so here's a little table that summarizes everything we've seen so far. So you can see, at a glance, sort of what the correspondences are between the first integer step model, then the steps where we took time steps of this rational 1 over n and just still had a discrete system, but at intermediate times, and then the continuous one. And it's quite nice to see just this correspondence in this, what is the comparison? And so how do you get sort of from one to the other, right? So for example, powers in the discrete world become often exponential functions in the continuous world. And differences, as Alan said at the start, differences in the discrete world become derivatives in the continuous world.
So when I first saw like this one, it kind of bugged me. Like, why can't you do like you did here? Like, why can't you just exponentiate? I mean, of course you kind of can, but you see that when delta t goes to 0, all you end up with, if I could write this with my mouse, is n of t is equal to n of t, right? It's 1 when delta, like it doesn't give you any information if you, I mean, you've got to put it in this, you've got to turn it into this form, or
that's right.
It's kind of like, it's sort of interesting that you have to manipulate it. And I guess if you see this 100 times, you'll see the manipulation is always pretty much the same. It's always turning a quantity to a change in a quantity, and that's sort of the key.
Yeah.
I mean, this is just representative of something you do all the time.
Basically, you can think of it as being, because if you think of this, if you look at this last line here, you have the change in n of t divided by the change in t. And as you take the change in t to going to 0, the change in n of t also is going to go to 0. And so then you're going to get 0 divided by 0 here. And that doesn't make sense. So you have to, so you have to do something, yeah.
It makes sense in a limit, but it doesn't make sense.
Yeah, I mean, that's what you're saying. You get 0 equals 0 if you put delta t equal to 0. That's a true statement, but not useful.
But not very.
So you have to actually take this limit in a more careful way, basically.
Right.
Yeah.
Good.
Okay. So let's look at a more complicated example. And in this more complicated example, which everybody probably has seen a lot recently, the SIR model of how an epidemic changes in time. So how the number of infectious people, in people infected with, unfortunately, with COVID-19, how you can model that change in time. So this will be just the simplest possible example of these models.
I'm wondering, what is the probability that an MIT course was infected with the SIR model? I think it's 20%.
That's an interesting question, yeah. So you can also think of this as, if you don't want to think about epidemics right now, you can think about the spreading of a rumor in a population instead. How does if somebody starts a rumor about some celebrity, how does that spread through their network of friends? And so so this is interesting, not only because it's very topical, but also because it's an example where you can write down a relatively simple set of differential equations that cannot actually be solved explicitly analytically like this. You can't write down a formula for how the quantity at time t depends explicitly on t. Okay, so how does this work? So you've actually been doing this for homework. And so you probably know about this already, and from reading the newspaper, etc., or the online newspaper. So agents are just people, and they can be susceptible, which means that they are available for the disease to attack them, and they can be infectious to start with. So let's just think about, how do you get from being susceptible to being infectious? Well, you do that by being in contact with somebody who's already infectious. And so let's call capital S sub t and capital I sub t the number of susceptible and infectious people at time t. And let's call the total number of people n, capital N. So how do you get to be infected by somebody? You can only be infected if a susceptible person and an infectious person meet. And when with some probability, the disease gets transmitted. The infection gets transmitted. So let's suppose that each infectious person at each time step, so we're going to have, again, time steps, discrete time steps, which we're going to think of initially as just days again. This is the same kind of process. On each day, we'll count how many people were susceptible and became infected. So we need to write down some model of how that happens. And so we're going to do something similar to what we did in homework, which is to say that each infectious person on each day will contact, let's say, for ease of argument, we'll be in contact with, we'll choose one person from the population to be in contact with at random. And so if that person that they contact if they are infectious and the person that they're contacting is susceptible, then it's possible for them to transmit the infection to that susceptible person. And that will happen with some probability, which we'll call little b. That's one way of thinking about this model. And a different way would be they're actually going to contact several people, and this b somehow models how many people they contact. So but each infectious person is choosing one person at random from the population to contact. And so they can only transmit the infection to a new person if that person is susceptible. And that will happen with a certain probability as well. And that probability is the chance that when I choose a person at random from the population, that person will be susceptible, which is the fraction of people that are susceptible. So capital ST divided by capital N. So again, we're going to look at the change in the number of infectious people after each day. So that we'll call capital delta IT, which is capital I at t plus 1 minus capital I at t. And so by this argument that I just did, it's actually equal to b times the total number of infectious people at time t times the number of susceptibles divided by n. So I get this capital IT comes in there because each infectious person in my model, in my assumption in my model, each infectious person is trying to sort of touch one person in the population, but they're choosing those at random without knowing whether they already have the disease or not. And so we get this particular form that's very common in all kinds of models where we have this product, multiplication of two of the variables, I multiplied by S. This is called a mass action type of model. It's an assumption that corresponds to what is often called a well-mixed population. So the population is all mixed up, and they're sort of at a primary school running around, and somebody has measles, and they all have a chance to interact with each other because they're running around the playground and playing tag, and so they're actually touching the other people, in pre-COVID times at least, and so they actually have this chance to mix up with everybody and chance to touch everybody in the population. This is an assumption. Okay, so for example, this could also be chemicals reacting with each other. And so if we have a well-mixed beaker of chemicals, we're actually mixing up the beaker, then everybody sort of has a chance to mix up with each other. If we don't have that, then we have a completely different model where we have the effect of space involved. And we'll talk about that later. So, okay, and so the number of infectious people is going to change. And when the number of infectious people changes, the number of susceptible people has to also change in exactly the opposite way. So anybody that becomes infected stops being susceptible. And so ST is also going to decrease by this same amount. And then we'll also add in recovery, which is something we've studied before, basically the same component failure model. So we'll have a constant probability C at each step for an infectious person to recover at that time step. And so, so then we can write all of those equations down, but it turns out that a useful way to write them down is just to notice that, oh yeah, it's probably useful to actually divide the total numbers of which are sort of occupying each class, S, I, and R, called classes or compartments. It's useful to divide that by the total number. So we get a sort of proportion of the population that is in each class, and they have to add up to 1. And so
with the light bulbs, you could have divided by N0.
Yeah.
And
I did think about dividing by N0 and having a proportion of the light bulbs that were, that's probably a good idea.
But it's not really required. It's just, whether you like to work with percentages or absolute numbers. You can solve it, I guess, either way.
You can, but actually in the computer, it's often useful to do that division, because then you're working with quantities that do not have a dimension. And for example, you actually will get the same curve. If you start with 100 light bulbs or you start with 1,000 light bulbs, you'll get the same curve once you divide by the initial number.
I guess that's the whole point of percentages, even from day one, right? That's what we talk about percentages.
Right. So so in physics, that's often called a-dimensionalizing your model. So you try to reduce the number of parameters that are in your model by making these combinations of parameters that don't have a dimension, that are dimensionless. And that will actually give you the sort of simplest possible form of the model. On the other hand, it also has disadvantages. Anyway, and Julia has this package unitful that I think we mentioned before, maybe, for calculating with quantities which do have units like meters or seconds, etc. Okay. So we now have these little st, little it, and little rt are these proportions of the population in each state. And putting all of what we've just done together, we end up with this formula, which is the discrete time SIR model. So it tells us how does ST evolve in time t, how does IT, the number of infectious people, evolve, and how does the number of recovered people evolve. And it's this sort of relatively simple looking system of equations, but it's nonlinear. It has this product term in here, right? So you cannot write this as a matrix. This is the sort of simplest form you can write this in.
But this is a recurrence as written in 3 variables.
Yeah, it's still a recurrence.
You were able to time step light bulbs and get n k plus 1. You can type SI and R in tandem and get the next days.
Yeah. So how can I actually solve, as Alan was saying, how can I solve this? What does that mean? It means calculate S of t, I of t, and R of t for each t. And so as Charles was saying, there's an infinite number of times t, countable infinite number, all the integers, positive integers, that I would like to calculate the result at. But actually I can't, because I don't have a formula, an explicit formula that tells me, oh, S at time t is the exponential of something to do with t. There is no such formula as far as I know. So because of this nonlinearity, if it were linear, I could write down such a formula, but because of this nonlinearity, I can't. And since almost all models are nonlinear, or all interesting models are nonlinear, we could say, basically you can never write down an analytical solution. And in fact, nonlinearity often also leads to chaotic dynamics that we probably won't have time to talk about, unfortunately, in the course. Just adding these kind of nonlinearities into a model like this often leads to chaotic behavior. Not in this model, I think. But
so in any number of courses, we do get students to solve recurrences that have analytic solutions. Yeah. But as you're saying, there's a very rich family where they don't have analytic solutions, but we don't have to give up.
there's a very small number that do have analytical solutions, is a better way to put it. And that basically they're when everything is linear. When everything is linear, you can solve them, and when everything is non-linear, you can't solve them. That's almost
That's a little too strong. Sometimes you can solve.
Okay, sure. But if they're non-linear, how do you solve them? You solve them by finding a clever transformation to reduce them to something that's linear. It's almost.
Or something that's recognizable.
Right.
Yeah. It doesn't have to be linear, but okay.
Okay, fair enough. Yeah, so there are isolated ones that are non-linear, but that you can solve. But basically, if you write down a sort of general one, you don't really have a hope of solving it analytically. But what can you do? You can solve it numerically. So here is a numerical solution of that. Just exactly taking this equation, this set of equations, and literally advancing it in time. So we start with some initial values for S, I, and R. So we'll have sort of 1 infected individual, 1,000 susceptible individuals, and 0 recovered individuals. We'll fix some B and C, which is just these rates. So I haven't actually used that word yet. I forgot to say that this P that comes into this differential equation is often called a rate, which means a probability per unit time. You see that in this continuous formulation, we have P multiplied by a time. And so P has to have the units of sort of probability divided by time, or per unit time. And so that kind of object is often called a rate. So in this equation, we have this rate P at which n is decaying.
It's not surprising, because in the light bulb example, your P was light bulbs per day, right? So
Exactly.
So we never said it out loud, but implicitly there was that time in the denominator. It was
That's
per
right.
day.
Yeah, and here you can see it explicitly as the sort of light bulbs per,
per n times per day, right?
Right.
Yeah.
Okay, so this you can you just literally program this recurrence into Julia, and it's something like this. This is exactly, I'm just transcribing those formulae into code, and it looks like that, where delta I is this probability of infection times S times I, and delta R is a probability of recovery times I, and you put them into the equations and just iterate that. And that gives you immediately a numerical solution for those particular initial conditions and those particular rates of recovery, P infection and P recovery. And that gives you some formula. And when I change, I don't have a slider here, but you could easily add sliders and change. Maybe we should do that actually. I could add sliders for those, and you just, exercise, add sliders for these parameters and see how does this change. So this peak here in the orange curve is, we're worried about the capacity of our number of beds in the ICU, because basically we have here nearly 75% of our population infected at time, after 80 days or whatever. Okay, but then what can we do? So from what we've seen in the first half of the talk, the lecture, what we would like to do is say, well, people don't just become infected at midnight each day. They can become infected at any time. And so it's actually more natural to write down a model in which we take small time steps and see what proportion get infected after each small time step. So we can go through exactly the same process that we did before. We would write down S at time t plus delta t equals S at time t minus B times S at time t times I at time t. Basically, we just rewrite this. Instead of t plus 1, we're going to have t plus delta t. But this B, again, then needs to become, let's call it beta, so beta multiplied by delta t. And then what we get is, I thought I wrote all this out, but I apparently didn't. Sorry. So we get S at t, let me write it out now. So we get S at t plus delta t equals S at t minus beta multiplied by delta t multiplied by st multiplied by it. And then what we're going to do exactly the same thing that we did last time, which is to put this S of t over to the other side, so we get this difference, the amount that's changing during the time step, and then divide by delta t. And so we get this fraction over here, the fraction of the difference of s of t plus delta t minus s of t divided by delta t equals minus beta times s times t. And then we recognize this as the derivative when we take the limit as delta t goes to 0. And so we end up with ds by dt at time t equals minus beta s at time t times I at time t. And similarly, so that's, S is decreasing due to this infection dynamics. I is increasing, the number of infectious people increases in the same way. And then we have this recovery process where each individual independently decides to recover at each time step with some other rate gamma, and the number of recovered people changes just due to that process. So we get this system of differential equations. So 3 differential equations, first order, that means first derivative only. Each of them is changing, but they're all coupled together. So, the way that R changes depends on I, the way that I changes depends on S, and the way that S changes depends on I. So they're all intertwined with each other or coupled together. And so now we would like to solve this differential equation. What does that mean? Again, it means find values of S at time t and I at time t and R at time t for all times t. So now t is a real number going from 0 to plus infinity, and we want to find a solution. What does that mean? It means we want to actually find the whole function s of t as a function of any real number t, and the whole function I of t, and the whole function R of t. And what I'm saying is that we cannot actually do that. We don't actually have an analytical solution that we can write down. So what can we do? We have to solve it numerically. Oh, there are other things you can do, but a natural thing to do is to try and solve it numerically. So how would you actually solve this equation numerically? So if we're given a differential equation, or somebody comes up with a differential equation model, and these are very common in science, physics, biology, chemistry, because processes in science happen at any moment. They don't usually happen in discrete intervals. In biology, you might have mating seasons, and it might be natural to talk about the number of insects each year, for example, but in physics, the position of a pendulum is changing continuously in time. And so it's natural, you naturally end up with models that are actually written as differential equations. But they, again, may be nonlinear, and so you cannot solve them in general analytically. So what can you do? There are various things you can try and do, but one of them is to solve it numerically. So how can we solve this differential equation numerically? And so what we're actually going to end up doing is, the only thing we can do is go back and turn this back into a discrete model again. So how can we do that? We're actually going to sort of undo all the hard work we just did. So basically go back exactly, trace back through this process that I just wrote down. So starting from this differential equation, we go backwards and we get to this discrete version of the differential equation, where we have taken a finite number, delta t, instead of the limit where delta t goes to 0, we're going to approximate that limit with a finite number, delta t. Finite meaning non-zero, non-infinitesimal. And then we go back another layer and we get to this equation. S of t plus delta t is s of t minus beta times delta t STIT. So this is now something that I can program into the computer. It just says at the next time step, we take the value of the previous time step minus the rate at which it's changing times whichever variables occur in that expression in the differential equation. So this is called the Euler method. And so basically, how do we solve an ordinary differential equation? We're going to do time stepping. So we're going to, as I said, undo the process that we've been doing through the whole lecture, where we started with a discrete system and ended up with this differential equation. If we're given a differential equation coming from some scientific problem, or engineering, or economics, etc., then we'll undo the differential equation. So we'll approximate. So this is a sort of general way that people often write a differential equation. X dot equals f of x. So dot here, I forgot to mention, means d by dt. Well, I won't bother writing it right now. d by dt of x. So x is some kind of position of a pendulum, for example, is some function of the position of the pendulum. So, or the how fast does the concentration of a chemical change? It changes due to its interactions with the other chemicals and the way it moves around and how fast it encounters other chemicals and how likely it is to react with them. And so, people will encode all of that into a differential equation. But now to solve it numerically, we're going to, as I said, undo this definition of the derivative into an approximation like this. So above I use delta t, it's very common to use h instead for the step size. So we're thinking of a small h, like 0.01 or something, and we're going to approximate the derivative by using that fixed small value of h. So approximately the derivative is going to be x of t plus h minus x of t divided by h. And then again, we rearrange the equation and we get x at the next time step, t plus delta t, sorry, that should be h. Let me actually change that one. Let's see. X at t plus h is approximately x of t plus h times f of x. So if we call those time steps, again, we go right back to where we started. We call them x at k plus 1 is actually at the k plus 1th time step of size h. Now, instead of size 1, then xk plus 1 is xk plus h times f evaluated at xk. And this is what's called the Euler method. And that can also work if, so for our SIR model where we have 3 variables, we'll wrap those 3 variables up into a vector, and then we can actually write the differential equation in a vector form. And the Euler method can also be written in a vector form and programmed like that in Julia or whichever language. And so, so this is sort of the first thing that you could think of doing, but it turns out that it doesn't actually work very well. Why doesn't it work very well? Because we've already seen that, basically, from these curves, this green curve is the exact solution to the differential equation, and basically the blue curve is some kind of Euler method approximation, and it does not actually approximate the curve particularly well. As I take a smaller and smaller step size, I get a better and better approximation, but actually, the rate at which this converges as I take the step size to 0 is actually pretty slow. And so it turns out that in numerical analysis courses, you can, for example, 18330, you can find out, we're actually about to start that tomorrow in 18330. So if you're interested, please let me know. Then, there'll be notes online. So you can actually find better methods. So if you're given a differential equation, you can find different ways to discretize it and replace it with a time-stepping routine, but which are better than the Euler method in the sense that they better approximate the continuous curve that is the true solution of the differential equation. So we have to say that, it's not even clear that when you write down a differential equation like this, you're telling me how fast the system should move when it's at a given position. It's not even clear that that is actually even has a solution, or sort of, does that even make sense? But you can prove that under certain technical conditions, it does make sense and it does lead to a curve. And what we're trying to do is actually calculate that curve. And so in general, one of the only ways we can do that usefully is by using a numerical approximation, using something like using time stepping, and that's more complicated than the Euler method, but the Euler method is a good sort of intuitive introduction to what that means. And so just to finish off, I'll comment that there's a big ecosystem collection of packages called differentialequations.jl, which has now been sort of renamed to SciML for Scientific Machine Learning. And this is actually a state-of-the-art library written in Julia that provides many different methods, numerical methods for solving ODEs very accurately, and also many other types of differential equations. And so if you need to solve differential equations for your research or your homework assignments, and you're not asked to program it yourself, then this is a very good option to actually.
We don't, as easy as it is to understand the Euler method, as Dave said, we don't particularly recommend it in many cases. Yeah,
no, definitely. It's usually not a good idea to use the Euler method. In this particular case, for this particular set of equations, the SIR model, it will give you a qualitatively good solution And it's good enough to sort of understand what the dynamics of the system is. But for example, if you have a pendulum and you try and use the Euler method on a pendulum, you'll find that it gives you the qualitative behavior of the solution is just completely wrong. Because a pendulum conserves energy, whereas the Euler method will not actually conserve energy. And so it'll just sort of, you'll have this pendulum that sort of starts accelerating and accelerating, which is totally physically wrong, basically. So that's one of the ways in which the Euler method is a bad idea. And so there are other methods that are more accurate that will correctly capture that kind of behavior. Okay, so thanks everybody. We'll carry on Monday. See you then.